Hello chemists, this is Ms. Placino and you're watching lesson 9.4 on calculating delta H. In today's lesson, as the title suggests, we're really going to be focusing on how to calculate changes in enthalpy, also known as delta H. Today's lesson is pretty calculation heavy, so make sure you've got a calculator handy and you might want your reference table as well. All right, goals for today's lesson. We're going to use reference table I to calculate changes in enthalpy. This is going to be what I call Regents style enthalpy, and it's pretty straightforward. It really just relies on your ability to read and interpret a table. Then we're going to do kind of real world style calculations where we're going to use heats of formation to calculate changes in the enthalpy of a reaction. Both of these are pretty important goals. This one kind of more geared for 10th grade. This one more of an advanced topic, but I know you can do it. All right, let's dig in. We first introduced the concept of enthalpy last lesson in relation to a potential energy diagram. We really just looked at it as the difference in energy between the products and the reactants. There's a little bit more to it than that. When we're talking about the enthalpy of a reaction, or the heat of the reaction, or delta H, again, just multiple ways of saying the same thing, we're looking at the quantity of energy transferred as heat during a chemical reaction. This does relate back to moles. We can use this really general equation that the change in enthalpy of the reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. We're going to be building on this concept as we go. All right, so we'll start with hopefully the easier of the two concepts. We'll be looking at Regents-style enthalpy questions. Table I in your reference table gives you a bunch of heats of reactions. They've kind of gone through and selected about 24 or so chemical changes and a handful of dissociation equations to provide delta H for. Reaction conditions can impact delta H values, so we usually do them at kind of STP. Well, I shouldn't say that. We do it at 1 atmosphere of pressure and about 25 degrees Celsius, more or less room temperature. You've got delta H's provided in terms of kilojoules, and we've got just a list of reactions. Delta H is proportional to the coefficients in the balanced chemical equation. For example, if we just take a look at, we'll just look at the first one, why not? The reaction between 1 mole of methane and 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. That reaction will produce, since it's a negative, so it's an exothermic reaction, about 890 kilojoules. If I cut all the coefficients in half, so I said like 1/2 a mole of methane, just 1 mole of oxygen reacting to form 1/2 a mole of carbon dioxide and 1 mole of water, since I cut all of my coefficients in half, I would also need to divide my delta H in half. If I tripled all of the coefficients, I would triple delta H. That's what we mean when we say delta H is proportional to the coefficients. Kind of the other little trick that we have to use with table I is if we reverse the reaction, we're going to flip the sign of delta H. So let's look at this equation here. We have carbon reacting with oxygen to produce carbon dioxide gas, and that process is exothermic and releases 393.5 kilojoules of energy. If I want to go in the opposite direction, so instead of the synthesis of carbon dioxide gas, I want to look at the decomposition of carbon dioxide gas back into its elements. Since I've changed the reaction direction, I'm also going to flip the sign of delta H. So if the forward reaction was exothermic, the reverse reaction has to be endothermic, and the sign of delta H would change. If you think about that in terms of a potential energy diagram, we saw an exothermic reaction in the forward, reactants to products. We'll see an endothermic reaction going in the reverse. And delta H, the numerical value isn't going to change, but the sign absolutely will. So let's try a couple practice problems with this concept. Let's take a look at practice problems. We'll go 1 and 2. So question 1 is asking us, what is the value of delta H when 6 moles of ammonia are produced from its elements? This is all about using table I. So if we take a look at reference table I, we want to find a reaction where we're producing ammonia, NH3, from its elements, nitrogen and hydrogen. So let's see if we can find that. Ooh, wow, really zoomed in. So we've got table I. Oh, look at that. We've got the reaction between nitrogen and hydrogen to form ammonia. So I've got my reaction, and I can see that with the coefficients provided, delta H is negative 91.8 kilojoules. So I'm just going to quickly jot down that reaction over in my practice problems. So I have N2 plus 3H2 yields 2NH3. My delta H is equal to negative 91.8 kilojoules. Okay, the question is asking, what is the value of delta H when 6 moles of ammonia are produced? Well, if I want to produce 6 moles of ammonia, what do I need to do with this entire equation? Hopefully you're thinking if we multiply everything by 3, we can get 3N2 plus 9H2 yields 6NH3. Whatever I do to the equation, I've got to do the same thing to delta H. So I can take my negative 91.8 kilojoules, multiply that by 3, and I would come up with a value for delta H of negative 275.4 kilojoules. I'm not going to concern myself too much with the significant figures at this point in the game. Just go ahead and solve the math, and just don't be ridiculous with sig figs. Try out question 2 on your own. How much energy would be needed to create 4 moles of carbon by decomposing C2H6? So I'll give you a hint. Use table I. You want to start by finding C2H6. So try it out. Check your work when you're finished. So I've gone ahead and I've looked up that reaction in table I, and I've got 2 carbon plus 3 hydrogen yield. I guess at this point in time, we'd probably call that dicarbon hexhydride or hexahydride. In reality, we would call this ethane, but that's for another time. Okay, I want to figure out how much energy is going to be required to create 4 moles of carbon. All right, so right now I've got 2 moles of carbon in the equation. I'm going to need to multiply this whole thing by 2. Right now, carbon is a reactant. I need carbon to be a product. So I need to reverse this reaction, ultimately producing 2C2H6 yields 4 carbon plus 8, math. Sorry about that, 6H2. Okay, so now it's producing 4 moles of carbon. I've got to do the same thing to delta H that I just did to my equation. I've got to multiply by 2. And I need to flip the sign since now I've got the reverse reaction occurring. So you can either think about that as multiplying by -1, or if you just want to go through and change the sign right off the bat, that's completely okay as well. So I can take 84 times 2, and I come up with 168 kilojoules as my amount of energy that would be required to create 4 moles of carbon using C2H6 as the reactant. All right, and that's kind of the gist of it. Question 3 has you doing kind of similar calculations, except for a physical process, dissolving ammonium nitrate. And question number 4 is a little bit trickier. It's going to try to pull in some stoichiometry in addition to thermochemistry. So give those a shot. All right, so what we just looked at is kind of a very Regents style question on enthalpy. On that table I, there are, again, a few dozen reactions listed. I hope it goes without saying that there are more than a few dozen different types of chemical reactions out there. So chemists in the real world obviously don't use reference table I. They use a very different set of tables called thermochemical data tables, and one of the pieces of data that can be found there is the molar enthalpy of formation, sometimes known as delta H sub F. That's like heat of formation, and that like little degree sign means at 1 atmosphere and 25-ish degrees Celsius. This is the enthalpy change that occurs when 1 mole of a compound is formed from its elements in their standard state at 25 degrees Celsius in 1 atmosphere. So don't concern yourself too much with the definition. I'm more concerned with the application. Just a little bit more before we get into applying this information. Elements in their standard state. And when we say standard state, it's basically what are they going to exist as, or like what phase at 1 atmosphere and 25 degrees Celsius. For example, oxygen exists as O2 gas. So the heat of formation of any element in its standard state, so it's like kind of phase and formula, if you will, at 1 atmosphere and 25 degrees Celsius, is going to have a heat of formation equal to 0 kilojoules per mole. For like a metal, monatomic and in the solid phase more often than not. Something that would not be an example of an element in its standard state is something like ozone. That is not in its standard state. This is the standard state for oxygen. The more negative the heat of formation is, the more stable the compound. And we'll kind of start to look at some examples of that. This is the formula that we're going to use to calculate enthalpy in quote-unquote the real world. Let's not get too intimidated by it. It's basically the same formula that we were using before, products minus reactants, except for being a little bit more specific. So we have the delta H of the reaction, the change in enthalpy, is equal to summation of moles of the products, subtract the summation of moles, enthalpy of the reactants. So go ahead and jot that down. Give you a little bit more information. Again, delta H of the reaction is the total change in enthalpy that occurs over the course of the reaction. This term here is the moles of products times, the summation, the enthalpy of the products. And as you might imagine, kind of a very similar looking term for the reactants, it's the moles of reactants times the enthalpy of the reactants. Probably the next logical question that you have is, where do these numbers come from? How do I start kind of, filling in the missing variables? N is the number of moles. Basically, we're going to use the balanced chemical equation and look at coefficients. Any H values are going to come off of our thermochemical data table. For most of our purposes, just to kind of save time, paper, and frustration, and to make sure we're all on the same page, I'm going to be providing you with heats of formation for products and reactants. It just will make our lives a little bit easier so you can focus on applying this formula and not hunting to try to find the numerical data itself. So let's go ahead and try to calculate delta H together. In this reaction, we have methane reacting with oxygen to form carbon dioxide and water, a reaction that we should be pretty familiar with at this point in time, as it's what takes place in our Bunsen burner. First order of business, go through, balance that equation. Hopefully balancing is becoming a little second nature. We see coefficients of 1, 2, 1, and 2. Directly underneath the compound and elements, I've provided you with the delta H value. So the heat of formation for methane, for example, is negative 74.8 kilojoules per mole. Oxygen is an element in its standard state, so it has a heat of formation of 0. And we've got carbon dioxide as a gas and water as a liquid. Which is the most stable of these molecules? The more negative the heat of formation is, the more stable the molecule is. So in this case, carbon dioxide would be the most stable of the 3 molecules listed. All right, let's do some calculations. I'm going to take my general formula. The delta H of the reaction is equal to the summation of moles, the H of the products, minus the summation of moles, the H or the enthalpy of the reactants. I'm going to break it down into multiple steps to try to make as much sense of this as we can. So my change in enthalpy for the whole reaction, and you'll see reaction abbreviated RxN a lot, is equal to my products, 1 mole of carbon dioxide times 2 moles of water, minus the enthalpy of my reactants, 1 mole of CH4, methane, plus 2 moles of oxygen. This is a step that maybe when you're first starting off, you might want to include to really kind of help you figure out how you're going to sub numbers in. It is very frequently skipped as you become more confident and comfortable with these sorts of calculations. The next step is to take these numerical values and plug them in to the appropriate compound. So for example, negative 393.5 kilojoules per mole, I'm going to sub in for carbon dioxide. I've left my units out just for simplicity's sake and to make sure there's enough room. But I've got my coefficient times my enthalpy of formation value. Coefficient times enthalpy of formation value. We don't technically need to show 2 times 0, but again, I'm trying to be really complete so you can see where all of these numbers are coming from. The math here itself is not complicated. It's multiplication and addition and subtraction. So not too challenging. What is really easy to do is to lose track of signs and to just make careless mistakes while you're typing things into the calculator. I cannot stress this enough. Work stepwise. Don't be afraid to show your work and write things down. So to kind of simplify my terms, if I take negative 393.5 and add 2 times negative 285.8, I'll come up with negative 965.1. Aside, substantially easier on the with the reactants, since we've got 0 as our heat of formation for oxygen, so minus 74.8. I'm going to go ahead and combine those. And I come up with negative 890.3 kilojoules, which is going to be an exothermic reaction. If you take a look back at table I, the first reaction listed is the, it's the same, it's the combustion of methane. And it gives you negative 890.4 kilojoules. So this is just another way, or kind of the real way, I guess, that you would get that answer. The fact that we're off by 1/10 of a kilojoule, don't stress about that. It probably comes from like how these numbers have been rounded. You can take them out to more places after the decimal point, but that seems pretty unnecessary. We know this is an exothermic reaction because delta H is negative. The sign is extremely important when working with enthalpy calculations. All right, I highly recommend digging into a practice problem or two with this calculation. I know I'm repeating myself, but the math itself is not hard, but it is incredibly easy to make small, kind of thoughtless mistakes, and then it just spirals into all sorts of calculation errors later. But I know you can do this, even though it's a little bit more advanced. Don't be intimidated by that formula. Go through, practice, and get confident. All right, chemists, that's going to wrap it up for today. Thank you for tuning in, and I hope you found this helpful.